Okay, so let's just talk, let me take a moment to talk about a little bit of comparative statics. I think that this discussion will give you a little bit more of a feel for the mechanics of a linear regression and how, sort of how this thing works. So, so I list them here, and I'll go through each one separately. If we have a larger sigma squared, so imagine having sort of two different data sets. They're identical, except for one of them has a larger error variance. How is that going to affect our estimates? Well, you can just look at the formulas for the variance and the covariance and so forth of our estimates. And you can see that if we have a larger sigma squared, that's going to mean that the variance of beta hat is larger. Okay? I'll show you a picture of that in a second. If we have a larger variance of x, so in other words, our x's are more spread out, that's going to lead to a smaller variance in beta hat. And a larger n also means a smaller variance of beta hat. And then furthermore, if the mean of x is positive, then we're going to have a sort of negative covariance, a negative relationship between beta naught hat and beta 1 hat. And I didn't write it down here, but if x bar is negative, then that flips, okay? So let me show you pictures of these, and that'll make the comparative statics a little clearer, I think. Oh, and I should say, just a point of notation. I'm often going to just start sliding into sort of matrix and vector notation. And when I say beta hat, I'm talking about the vector beta naught hat and beta 1 hat. Okay? Okay, so what's the first comparative static? What does that suggest about the mechanics of the regression? So we have two identical data sets. The only difference is that the error variance is greater in one. What does that mean? That in this case, we're going to be less sure of our estimates. The variance of beta hat is greater. Okay? We're just going to have less confidence in our estimates. That makes sense, right? If we have very small error variances, we're going to be able to estimate that linear relationship very precisely. How about if we have the same data sets, but in this case, the x's on the left are very spread out. We have a lot of variation in the x's. And in the other case, the x's are all smushed together into one little area. Well, in the case where they're all smushed together, remember in the limit, we can't even estimate our linear regression coefficients, right? Remember the picture I showed you in the beginning where all of the observations on x were on a single point? We couldn't even estimate the linear regression coefficients there. Here we can estimate them, but the variance is going to be pretty big. We're going to be less sure of our estimates in this case because we don't have a lot of variation of x to help us identify the effect we're interested in. Okay? A larger n means a smaller variance of beta hat. Well, I don't need to draw a picture of this. We'll just note that this follows from the fact that beta hat are consistent estimators. Okay? And then finally, there is this mechanical relationship between the two estimates. So if we have, for the mean of our x's is positive, then basically if we sort of overestimate the intercept of the line, we're going to underestimate the slope, or an overestimate of the intercept is associated with an underestimate of the slope. An underestimate of the intercept is associated with an overestimate of the slope. Okay, so it's just this mechanical relationship, and then if x bar is negative, the mechanical relationship shifts. Okay, or flips.